Hello there, and welcome to our next talk here. You'll see that this talk is actually really quite similar to the one that you will have just watched, which was all about hydride reductions. We saw molecules like this carbonyl be reduced by this hydride reagent nucleophile, kick the electrons up onto the oxygen and give you eventually an alcohol. What we're going to look at today is something called the Grignard reaction, which is actually very, very similar to what we have down in the corner there. The only difference being the identity of the nucleophile. In fact, if you look at the two reagents here, you'll see they are laid out in a very similar way to the way they were in the hydride reduction. Two steps, two individual steps, one after the other. H3O plus as the second step, implying some sort of protonation, which actually is what's happening. The only real difference is the identity of the nucleophile, and I know right now this probably looks rather strange to you, so let me give you a little bit of info about what this actually is. You've never seen carbon bonded to magnesium before. It's actually not a very common species, outside of Grignard reagents at least. And the reason why it's so reactive is magnesium all the way over on the left-hand side of the periodic table is actually very electropositive, and even more so than carbon, which puts carbon in something of an unusual situation. Usually, carbon is the electropositive species because whatever it's bonded to is more electronegative than it, and an example of this carbonyl would be that. Here, though, it's different. Carbon is actually the more electronegative element, and so what that means is in a molecule like this Grignard reagent you can actually show that that molecule can be represented by something that looks like this: CH3, CH2 minus. In other words, nucleophilic carbon. What that means for this reaction is it's going to be exactly the same as this one, except my nucleophile is going to be CH3, CH2 minus rather than H minus. All right, so here's my CH3, CH2 minus. What it's going to do is exactly the same thing as the H minus did. It's going to send its electrons up into the carbonyl, kick the electrons up onto the oxygen. And in exactly the same way as it did for the hydride reduction, it's going to form an intermediate that we'll call an alkoxide, the same as we called it before. The only difference here is now we've actually added two carbons into our molecule, these two shown in red here. So once we've made our alkoxide, the O minus, as it did before, just grabs the hydrogen from the H3O plus in that second step. All right. And what that then does is just give you your alcohol product. And then, for all intents and purposes, it is the Grignard reaction, very similar to the hydride reduction. The thing that's of particular note here, though, is look at the type of alcohol that I formed. And when I say type, I mean primary, secondary, tertiary. You can see here, of course, this is a tertiary alcohol. One carbon next to the carbon bearing the oxygen. Two carbons, three carbons next to the carbon bearing the oxygen here, hence tertiary. Look at the number of carbons we originally had on the carbon bearing the oxygen. That was 1 and 2. So this whole process really has involved adding one extra carbon, which has been these two. So you go from a ketone in a Grignard reagent always to a tertiary alcohol because you're adding one more carbon around the carbon bearing the oxygen. You can actually make secondary and primary alcohols this way. The only thing you have to bear in mind is how you vary your starting carbonyl molecule. So let's say we're going to keep our Grignard reagent constant. And actually, whilst we're talking about that, let's talk about the name of this a little bit. Okay. We can just name this simply by naming the alkyl group as we would name it as a substituent. Okay. So ethyl, Mg of course is magnesium, and Br we're going to name as a substituent, so bromide. Ethyl, magnesium, bromide. So all Grignard reagents can be named in exactly the same way, you just need to know the name of the nucleophilic carbon group. Okay. So ketones make tertiary alcohols. You originally had two carbons around the carbon with the oxygen, then you've got three, so it's tertiary. If you were to want to make a secondary alcohol then, with 2 carbons around the carbon bearing the OH, how many carbons would you have around your carbon with the oxygen originally? Well, that would be 1. Now, what molecules do you know that have a carbonyl group and 1 carbon on it? And of course that is an aldehyde. I'm not going to go through the whole mechanism here, just as we did on the last slide, but you can see exactly what's happening. The CH3CH2- comes in, attacks the carbonyl, kicks electrons up onto the oxygen, forming the alkoxide, which then protonates to give you, let's see if we can draw out the product here, okay? We're going to keep our hydrogen, and this is your choice as to whether you keep this hydrogen here or not. That's totally up to you. The carbonyl has been replaced by an OH after our reaction's over, and we've added in our 2 carbons. Now look at what sort of alcohol we formed here. You can see this is secondary. It's exactly what we said it was going to be. All right. We took a molecule with 1 carbon next to the carbon with the carbonyl and ended up with 2. So in effect, we added 1 carbon, just as we did last time. But what if we wanted to make a primary alcohol? If we wanted to have a primary alcohol here and we had to add 1 carbon, that would imply a carbonyl group with a carbonyl here and no carbons either side of it. So then, well, what's that? What's a carbonyl group with presumably just hydrogens either side of it? Well, what it actually is the smallest aldehyde around. You'll know it when you hear what it's used for, unless you know it already. It's used for preserving dead tissue. This, of course, is the smallest aldehyde known. This is formaldehyde. Okay. So, exactly the same mechanism. Our CH3CH2- comes in, attacks the carbonyl, kicks electrons up onto the oxygen. The alkoxide that we form protonates. And once again, we can draw out our product. So I'm going to keep the 2 hydrogens here, just so you can see exactly what we're forming. We formed an alcohol here, and we've added on those 2 carbons here. Now notice what sort of alcohol we've formed here. This is a primary alcohol. And that came from formaldehyde. So I'm just going to go back a couple of slides here, just to summarize. If you want a tertiary alcohol, you start with a ketone. If you want a secondary alcohol via a Grignard reaction, you start with an aldehyde. If you want a primary alcohol via a Grignard reaction, you start with formaldehyde. Okay, that is the essence of the Grignard reaction. But let's move on, because all we've dealt with so far are aldehydes, ketones, and formaldehyde. The Grignard reaction actually works just as hydride reductions do with other functional groups as well. One in particular, and that one in particular is esters here. Okay. Now, one thing I'm not going to go through in a huge amount of detail right now is the mechanism. All right. But if I was just to draw out my CH3 CH2 minus, okay, I made that mistake again, so let me just erase that. Okay, if I have this and I have my species here, we know that's going to go in here, kick electrons up to the oxygen. Now, something different happens here. Notice there is a 2 in front of the Grignard reagent. Now, what do you think that means? Well, as you would imagine, what it means is this uses 2 equivalents of a Grignard reagent. Second step is protonation, as it was before. But what's different? Why do we have 2 there and we only ever had 1 for all the others? Well, what it is actually to do with is the fact that this is the only molecule we've seen so far that has something that can be a leaving group. All right. Let's see if we can push some arrows here. So I said we weren't going to go through the mechanism, but I guess I lied. Let's see if we can take a look at it. Okay. The electrons go up here to the carbonyl, same as we've seen before. Nothing new here. Okay. And we get our alkoxide. Okay, so we have our O-, all right. We have this guy, and we have the 2 carbons that we've just added on. All right. Now what's different here is that at this point in all the other reactions, this O- just grabbed the hydrogen because it had nothing else to do. One thing you'll see is that whenever you form an alkoxide in O- like this, it always has 2 choices. It can either protonate, or it'll do something else before it protonates if it can. And that is take the electrons back down to the carbonyl and kick out a leaving group if there is one present. And in this case, there is one present, which is this. So the fact that we had an ester here makes our reaction a little bit different, because we kick out that leaving group, and notice what we get after we've kicked that leaving group out. Because here we have 1, 2, 3, 4, 5 carbons with a carbonyl in the middle after we've kicked this out. So I'm going to draw out my 5 carbons with the carbonyl in the middle. All right. And I have my methoxide ion here, which is just kind of hanging out. Those should be 2 lone pairs there. But then I have my second equivalent of my grignard. So I'm going to draw that on here. CH3, CH2 minus. All right. Now notice what functional group I've formed. I've actually formed a ketone. And you've already seen what happens when I have a grignard reacting with a ketone, so I'm not going to go through the mechanism here, but I'm going to draw the product out. We can see that this just goes up here, kicks the electrons up onto the oxygen, and I get my alkoxide. Now with the alkoxide that we form here, are there any leaving groups that can come off? Well, in this case, as we saw with ketones normally, the answer there is no. So the O- does the only thing it can do, which is protonate. And let's see if we can draw out the product. All right. That's where our carbonyl group was, so it's where the alcohol is going to end up. But also, I have my other 2 carbons. All right. So in effect, I've added 2 Grignard reagents across my double bond. What sort of alcohol have I made here? Well, you can see it is a tertiary alcohol. What that means is anytime you have an ester, you always want 2 equivalents of your Grignard, and you will always get out a tertiary alcohol. All right, and that is the essence of a Grignard reagent with a tertiary ester.